Hi, everyone. It's 6 o'clock. Welcome to Mass Timber 101. I'm Carol Willis. I'm the director of the Skyscraper Museum and also the curator for our new exhibition, which you're seeing behind me in the gallery, called Tall Timber, The Future of Cities and Wood, and exploration and examination of a little bit of the history of mass timber, which is it's a short history, especially in North America. Only about 10 or 15 years old, a little bit longer in Europe. And it's a concept which has a tight-knit community of people who know a great deal about the varieties of mass timber. And we have two people to introduce us to that lexicon in Mass Timber 101 tonight. So I'm here in the gallery sitting at the materials table, and I'm going to hoist up this CLT panel, which you can see the edge of there, the Cross Laminated Timber. You can touch this in the gallery. You can also see other samples like my glue lamb right here, where all of the fibers go in the same direction. And to, I hope, come down and get a good idea of some of the remarkable buildings that have been constructed in this really revolutionary new material. And the people who are going to explain it to us tonight are themselves structural engineers, Michelle Roelofs and Tanya Luthi. And maybe I'll ask them to come onto the screen now with their cameras, because as a little bit of a round robin, they will be presenting the basics of mass timber and also talk about some projects that they've worked on. So Michelle is an engineer at the international engineering firm Arup here in the New York office. And she's been here in New York for some time, and she's actually going to talk about one of the briefly, as a case study, one of the projects that's in the exhibition and that she worked on. She actually worked on both of the winning projects of a 2014 innovation design study, a tall timber innovation designs competition. And we're going to have others of those teams in this semester of a look at mass timber in execution and kind of in its many dimensions in other of the lectures, which are being formulated now. They're not on our website, but keep track of this. What we're having this month is the fundamentals. And I hope those of you who didn't have a chance to see Lindsay Wickstrom talking about designing the forest and the book that she's written, but also the concept of managed forests last week, can now go to our website and find that archived video and learn how we started the forest before we begin to fabricate the wood here. Tanya is also a structural engineer. She's practiced in Vancouver in the Pacific Northwest. She'll talk a little bit about that with the engineering firm Fast & Epps, but she's now the director of engineering at Timberlab, which is a company that specializes in mass timber and part of Swinnerton, the construction company. So from the perspectives of designing and then of actually moving from the design into the material fabrication of the parts and the construction are parts of the profession that are represented by our two engineers tonight, but who have a great grasp of the whole industry and are going to take us through Mass Timber 101. So Michelle and Tanya, please take it away.
Thanks, Carol.
All right. Thank you, Carol. All right, I'm just going to dive in. Tanya and I are looking forward to presenting this today. Just a very brief intro to our work. I'll cover some of the mass timber basics, while Tanya will go into some of the key considerations when designing with timber and building with timber, and then we'll each give a brief case study.
So I'm a structural engineer for almost my whole career up to this point, almost 20 years. I was on the design consulting side, and after a stint living in Vancouver, British Columbia, started working on mass timber projects and really just fell in love with them. And then as my career progressed, just kept getting more and more into the mass timber world. And last year, I made the move over to Timberlab. So we are We think of ourselves really as a service provider. We're a contractor, but we really think of ourselves as a partner, a mass timber partner. So taking projects all the way through from pre-construction. So we do things like, cost estimating and scheduling and delegated design. So we can do the engineering. We do all the 3D modeling, shop drawings, procuring the mass timber, fabricating it in our 2 facilities. We have one in Portland, Oregon, and one in Greenville, South Carolina, where we have some CNC machines where we do the fab. And then we have installation teams that travel all over the country. So we really try to give people an integrated package to help get these buildings off the ground. And it's our, we're very mission driven. I'm really trying to get, mass timber to grow, especially in the US market.
Great. And I'm Michelle Roelofs. I've been at Arup for 15 years. I'm a structural engineer. And, Arup has been working on mass timber projects for a long time. And we have, dozens of projects across the world, with many of the first projects happening in the UK and in Europe. And then now we're seeing much more of that in North America. And, my background's structural engineering, but you'll see as part of this presentation that the design of timber really is very multidisciplinary, and looping in, fire, sustainability, acoustics, and we rely on our, colleagues who have this expertise, and then you also have to kind of get some of the expertise yourself, which is what we'll try to share a little bit of that today. So diving into some of the basics, I do like to start with saying what is not mass timber, because there's, can be a lot of confusion. So this, light frame construction, sometimes referred to as balloon framing, has been around for a really long time, very common in single family homes or in multifamily residential, kind of low rise multifamily residential. And so you still see a lot of light frame timber construction all over. And it's a very efficient way to build single family homes. And there's nothing necessarily, wrong with this type of construction, but it's just not what we're talking about when we're talking about mass timber. And a big distinction is that light frame construction, as you can see, there's a lot of very small and closely spaced members. Mass timber, there's an actual definition for heavy timber or mass timber in the code, and there's a minimum dimension that is required for different, a column, a beam, or a floor to qualify in this kind of mass timber category. And that is really related to its fire performance, which we'll get to later. But I just want to set the scene that we're really talking about this. We're not talking about light frame construction. And, it's also not exactly new. It's back, at the turn of the century, there were a lot of mass timber buildings, some of the big warehouse buildings that you see on the waterfront in New York, and I'll show in a moment. And at the time, it required the logging of very large trees, so you could cut out solid, columns and beams to create this heavy timber construction. So a good example is Empire Stores in Dumbo. For those that are in New York, you can see on the right some heavy sawn timber elements and the columns and beams there. And that was, a kind of historic heavy timber structure. Another example in Minneapolis from the early 1900s of a really nicely restored building that was converted to office space, has a lot of this really beautiful exposed solid sawn timber elements. But then, there really was kind of a decline in this type of construction for a lot of reasons. Steel and concrete became much more popular as a building material for large scale projects. But around the early 2000s, there was a bit of a shift and a back to some of larger timber elements. And so back in Minneapolis, about 100 years after that project was, that historic project was completed, was one of the first modern mass timber buildings in the United States, at least, which is T3 by Michael Green Architecture. And you can see that as a typology, it looks really similar to some of those historic projects with, big wooden columns and beams. But as a distinction, these are not single solid pieces of timber cut out of a tree, but rather engineered timber made from smaller parts and epoxied together. So, when you look at sawmills from early 1900s versus now, in the early 1900s, we're really relying on really large elements to be able to cut large solid columns and beams, whereas now, and this is a picture from 2016, kind of contemporary with T3, we can use significantly smaller, younger growth logs and cut them into smaller dimension lumber and then put them back together into these engineered products. So whether that's by epoxy or mechanical methods. There's also been a progression more recently of what we are able to do out of timber. So many of those historic projects are kind of up to 6-7 stories. When these new engineered materials started coming out, we've seen a bit of an explosion in how we can use the material, and there's been a progression in height and typology. This is from the Council of Tall Buildings and Urban Habitat. One thing you'll notice is that many of these early examples are either in Europe or in Canada. So we're seeing a lot of leadership happening from overseas. And this shows that another research done by Council of Tall Buildings and Urban Habitat that 54% of these tall timber projects are happening in Europe and 32% in North America, and it's not broken down more distinctly, but much of that is Canada. And another notable piece of data is that most of these projects are some sort of hybrid of timber and concrete, timber and steel. Like, these are often composite buildings, and that really is, I think, the future for these larger, taller timber elements. And another just kind of collection of some of these taller buildings that we're seeing. And again, if you look at this is mostly overseas. There's a few more recent examples from the Americas that are missing, but this is, a lot of the height is happening overseas. But to get back to some of the basics of what mass timber actually is, just to get into the terminology, I think there sometimes is a bit of a conflation between CLT and mass timber. There's a lot of acronyms, so I'm going to try to just very quickly break down that mass timber is kind of an umbrella term for a lot of different products and timber types, engineered timber types that fall into that category. So there's glulam, which is not a new material. This has been around since the 60s in the US, and there are some examples of this in churches across the country, those types of buildings. And this is dimension lumber laminated together in one direction, usually used for beams and columns. Cross laminated timber is kind of the newer material on the scene from the early 2000s. And this is similar in concept, where you take dimension lumber and glue it together, but in this case in alternating 90-degree patterns, which creates these dimensionally stable panels that can be used for floors and walls. And between glulam and CLT, you can have a pretty efficient building system. There are also a lot of composites out there. So timber concrete composites as an example, nail laminated timber. Actually, Tanya was one of the authors on a nail laminated timber design guide out there, which is the dimension lumber that's kind of nailed together. This is an older typology, but we're seeing it in some of the newer buildings. Dowel laminated timber, similar in concept, but connecting these dimension lumber using timber dowels rather than nails. Laminated veneer lumber, which is taking thin sheets and epoxying together. Laminated strand lumber, which is even smaller strand material laminated together. Mass plywood panel, another product that can sometimes be interchanged with cross laminated timber and how it's used. And this is a space where there's a lot of new products kind of being developed. So there's still innovation happening in just the materials that are available in mass timber. There's, now that we've given a few definitions, there's the question of, why has timber kind of taken off as a material? And there's a lot of reasons, but one of the big ones is a focus on embodied carbon in the built environment. So embodied carbon is the amount of energy, and i.e. carbon, that is used in the production of the materials that we use, the production, transportation, and full life cycle of the building materials that we use, or of anything that we use. And there's definitely been more emphasis and more focus on what where is the embodied carbon coming from in our buildings? And if you look at a typical building, about 70% of the building has some component of it that could be affected by considering timber, but the superstructure at almost 50% being the biggest component. And when you're thinking about embodied carbon, you're really going from the actual extraction of the resource through manufacturing, construction, use, all the way through to its disposal and its end of life. And we have our kind of more standard building materials, which typically are all in this mineral-based world, concrete, steel, other sorts of like gypcrete insulation, and these all emit carbon during the heavy industrial processes that are used to make them. We are now looking at a bit more emphasis in what we call bio-based materials, so materials that are natural in how they are grown and that actually sequester carbon during their growth cycle. So timber, if we look at a quick quick life cycle of a tree, for example. So as you plant it, there's some energy in the actual planting of trees. That's where you're kind of above the line here. Then as a tree grows, it's taking CO2 out of the environment, changing it into oxygen, and therefore sequestering carbon. So that's this kind of downward, this negative line that you see here. Then when a tree is cut down and manufactured, there's energy in that process that's used. So a bit of carbon emissions there. As it's once timber material is in a building, it is now dormant for the life of that building. But then when you get to end of life, there is an opportunity for that carbon to get back into the environment. So depending on how it is treated, incineration would kind of go straight back into the environment. If you're in landfill with methane capture, there's kind of a slower release into the environment. For the benefit of time in this presentation, I'm not necessarily going to go through all the other benefits, but there are benefits in the speed of construction for timber, for mass timber elements. There's various climate commitments that a lot of companies are trying to meet these days. There's a lot of policy coming out. In many parts of the US, there is a kind of surplus of forestry that could use a kind of a market. So there's some like rural workforce support. And there's also just the aesthetic benefit of having, timber in your building. And here's where I will hand over to Tanya.
So I'm going to talk a little bit about some of the things that make designing a timber building unique. I started my career very focused on steel and concrete. I never took a wood course in school, so I had to sort of unlearn a bunch of things or just learn how to kind of change my mindset a little bit because there are some things that are unique about timber. There are a lot of them. We don't have time to get into all of them, but I'm going to talk about a few of the ones at the top of this list. Mainly fire and code, and then talk a little bit about the connections, which is really, I think, what makes these buildings so fun. There's other things about acoustics and 3D modeling and durability that are relevant. If you have questions, you're welcome to submit them in the chat, and we can talk about them at the end. But fire comes up very often in discussions about wood buildings. For a lot of people, their first instinct is, well, why would we build big, tall buildings out of wood? Wood burns. And it is true that while timber is a combustible material, right, which means that it does, the material itself gets consumed in a fire. And our codes make a distinction between combustible and non-combustible construction. I'll talk about that in a little bit when I talk about the codes. But just because something is a non-combustible material doesn't mean that it's fireproof. I think there's sometimes also a misperception of like, well, as long as it's non-combustible, then it's good, right? But structural steel, as a prominent example, like doesn't behave very well in fire if it's not protected. That's why we spray it or paint it with intumescent paint. And so really every material, even concrete, right? Because concrete is always reinforced. We need to make sure we have enough cover on that rebar so that the steel rebar doesn't heat up too much and cause things to crack and spall. So no matter what material you're designing with, you need to think about how that material is going to perform in a fire. And so it's just sort of different ways of coming at the same challenge. And so what is unique about timber, and again, because we're not talking about, Michelle showed at the beginning of the presentation, these kind of stick frame structures that that a lot of people think of when you say timber construction in North America, because that's so much of our single family housing stock. Right. The analogy that a lot of people draw is with a campfire. So when you're trying to start a campfire, you want to start with a lot of small pieces. You want to start with kindling, small pieces with a lot of air around them. And that's what really allows the fire to get going. If you tried to start a campfire with a log and you just held a match to the log, nothing is going to happen. So when you have these very large, solid cross sections, they behave very differently. Rather than just acting like a pile of kindling and kind of going up in flames, you have this char behavior that once it does ignite, you need a pretty significant heat source to get it going. Once you do get it going, the wood forms a char layer on the outside. And so everyone has seen this if you've ever built a fire in your fireplace or seen a forest after a forest fire, that black layer that forms around the outside. And essentially, I like to think of it as sort of nature's version of intumescent paint. So on steel, when we put intumescent paint to protect it, that intumescent paint, when it's exposed to heat, it expands and then forms an insulating layer to help protect the steel from getting too hot, limits the temperature rise. And this is essentially a very similar phenomenon, just a natural one. So that char layer is also sort of an expanded layer that forms an insulation layer around the steel, keeping the inside of the wood cool and retaining its structural integrity. So generally speaking, you are just, because we understand pretty well how that char moves into the timber over time, we can design for it. So we know if we need a 2-hour rating, we're often designing for essentially to put some sacrificial layer around the timber to account for that char layer. Now, because we are often, Michelle talked a little bit about the different types of mass timber products that are out there. They don't all behave exactly the same, depending on how they're laminated. So particularly things like nail laminated timber, right, where you have all those really small pieces that are being nailed together. If you see the picture on the bottom, the behavior on the left is what you want. You want you want it to act like a big solid section. You need to be really careful about things like gaps opening up so that you're not charring the sides of those little members as well as the bottom. So there are some subtleties, but in general, you're just sort of taking a big solid section and subtracting a certain amount of char to do your checks for your fire case. Now, one of the phenomena that is becoming, getting a lot of attention in the fire research world, and when I talk a little bit about in a minute about what the code now permits you to do in terms of heights, the taller you go, the more they make you cover up the wood, or they make you encapsulate it behind essentially drywall or other non-combustible finishes. And the reason for that is, this is one of the unique things about timber, because it is a combustible material. We do have to be careful about, especially if we have sort of small compartments with a lot of exposed timber. And there's been a lot of research doing not just like what I'll call sort of full-scale fire tests. So not just a furnace test like you would do with a component like an ASTM E119 for those of you who are, do that kind of thing in your design lives, where they just stick something in a furnace and let it burn for 2 or 3 hours. Like this is what happens with a real fire in a real room, is you'll get this, ideally what you want is what happens in the graph on the left. Like something in the room sets on fire. Eventually everything in the room that is combustible will light on fire, but eventually the fuel, all the fuel gets consumed and the fire dies out. And that's really what you want for safety reasons in a building. You want the fire to not continue, so that if the sprinklers don't work for some reason, or the fire department can't show up, eventually the fire is going to die out on its own. If you have a lot of timber that is in close proximity, so say like a ceiling and a wall, or 2 walls that are next to each other, they can sort of re-radiate heat onto each other and create this phenomenon where the fire will not self-extinguish. And so this is why you see in taller buildings limits on how much timber can be exposed. I'll talk a little bit about that in a second when I talk about the code. But this is kind of a unique thing in the world of timber and an area of a lot of research. This ties very much into the code. So historically, I'm only going to go back. When I say historically, I'm just going to go back to 2000 when we started the first version of IBC, which consolidated all of the many, many codes that we had sort of regionally throughout the US. And so you see that there is, the code, again, this non-combustible versus combustible. You have type 1 and 2, which is the building elements are primarily non-combustible with some exceptions. And then types 3 through 5, where you are permitted combustible material for some or all of the building elements. And you'll notice that what's unique about, so type 4 has historically been the heavy timber construction type in the code. And really the provisions for type 4 HT, as it's now called, were really to describe those older heavy timber buildings that Michelle showed, that you typically got load-bearing masonry exterior walls, and then they've got these big solid sawn columns and beams on the inside. And so you'll see that what's different about these is if you look at these fire rating requirements, type 4 is the unique one. There are really, with the exception of exterior walls, which are not timber in this case, it doesn't actually have a rating. It doesn't have a time rating. It's not like a 1 hour or a 2 hour. It's just by nature of these minimum sizes. Michelle showed some of them earlier. So again, this construction type, sort of a description of the historic way we used to build with heavy timber. So, non-combustible exterior walls, and then minimum size requirements, and then your fire rating. I sort of say it in air quotes because it's a little different than the way we normally think of a fire rating with a time to it. Just historically, we know that buildings with these large sections have some inherent ability to resist fire. So as long as you provided those minimum sections, that's all you needed to do to qualify as type 4. And then typically these buildings, depended on your occupancy, but you were capped out at 6 stories and 85 feet. What was a little different about, type 3 and type 5, which also allows for combustible material, that the area limits are typically quite a bit larger for type 4 than for the other construction types. Then eventually, once we got to 2015, this is where you saw the first introduction of CLT into the I codes. So cross laminated timber. And this, again, because this is glulam had been in the code pretty much from the beginning, but CLT really sort of opened up a lot of new possibilities for how we build in mass timber, walls, dimensionally stable panels for floors. So it really was one of the things that started to jumpstart mass timber construction in Europe and the US. So 2015 is the first edition of IBC to talk about what we think of as modern mass timber or CLT. And then in 2021 was the really sort of sea change in the code, where the ICC Ad Hoc Committee on Tall Wood Buildings was formed. There was some very rigorous testing that was done in support of these code changes, but essentially the code introduced 3 new construction types. So the old type 4 was relabeled type 4 HT, and all of those provisions essentially stayed the same. And then we had these 3 new types, and for each type, the taller you got, the more timber you, again, as I mentioned before, you had to cover up behind non-combustible finishes. So for type 4C, you could go up to 9 stories and 85 feet. I've never figured out how anyone is supposed to fit 9 stories and 85 feet, but anyway, you could leave all the timber exposed in a type 4C building. In type 4B, you can go up to 12 stories, but only some of the timber could be exposed. And then in type 4A, you could go up to 18 stories and 270 feet. But in that case, all your timber is, none of it is visible. It's all hidden behind finishes, typically, non-combustible finishes like drywall. So, so this is, you see, this was a really big leap that has sort of allowed for these taller buildings, and you'll see the code continue to evolve. So for example, from 2021 to 2024 IBC, in this type 4B construction type, this middle one that you can go up to 12 stories. In 2021, you could only expose 20% of your soffits of your ceilings. They did some further testing between 2021 and 2024. And in 2024, you can now expose 100% of your ceilings. And again, this harkens back to that concern about, self-extinction and how does the fire really happen? And so, you can see things progress, which is kind of interesting. So again, if you see now the new table in 2021 IBC, and if you look at the new type 4s, they're actually quite similar in terms of their fire rating to type 1. So these are relatively stringent, like a 2-hour fire rating. You will typically be upsizing timber members to get a 2-hour fire rating out of them. But at least now there is a prescriptive code path for doing these taller buildings. Talking about connections also tend to be very unique in timber. A lot of times the connections are really what drive the whole design. I've early in my career made the mistake of, sizing a beam just based on bending moment and then going to do the connection and realizing that I couldn't fit all the fasteners in there. So it's really, I've always liked, one of my engineer friends also said something like, buildings are a bunch of connections that happen to have beams and columns in between them, which I've always liked because this is really where it's at, especially in a timber building. And so it's, for one thing, really understanding how these things get fabricated, what the tolerances are. There's sometimes a perception that because it's being cut with CNC machines and people think, oh, well, it's being cut with a robot and everything's going to be absolutely perfect and, 1/10 of a millimeter tolerance. And that's not quite true. Like, it is very precise, but there are still realities to the machines that we use. This to me is the most fun part of my job now that I work for a fabricator, is like, I'm an engineer, but I can call up the person who operates the CNC machines and I can have them explain to me, like, what is efficient to cut and what can we cut and what can't we cut, and just understanding the different tools that we have and how they work, and how to design around those fabrication realities, the tolerances that you need to account for, is a really big part of doing these connections successfully. And generally speaking, a lot of people ask, well, how do you make these connections? And there's sort of 3 general broad types of connections that we use in mass timber buildings. There are what we call sort of off-the-shelf pre-engineered connections. And so these are, typically come from a manufacturer. They've been tested. So the manufacturer can give you, an ICC report that gives you a maximum load that can go for a beam to beam connection or a beam to column connection. The nice thing about these is that they are, they're very easily concealed. So they give you a very nice, clean aesthetic. If you do need a fire rating, it keeps, you can keep all the steel components kind of inside of that timber char layer, which preserves that fire rating. You need to fire rate not just your member, but also your connection. Again, because these are off the shelf, it's typically kind of short lead times. You don't need special fabrication. You need to think a little bit about how you want to, how you want to recess. Like, do you want to recess it into the column, recess it into the beam with a plug and all these kinds of things? But again, they go together really nicely. They don't give you a ton of tolerance because they are pretty tight. So you do need to take care. Like, it's a little bit more difficult to do this, connecting to, say, a concrete wall, which might not be quite in the right place. But these are getting more and more popular, and more manufacturers are coming out with sort of different versions of these types of connections. And then if you're going to go the custom route, there's sort of the custom steel fabrication route where you're just kind of welding together a bunch of plates and screws and bolts. And, this is, you need a good metal fabricator to make sure that the metal pieces are being fabbed to the same tolerances as your timber, making sure everything is going to line up correctly. Just a couple of examples of what those kinds of connections typically look like. And then, where we can, we like to, although it's more complicated on the CNC fabrication side, but where we can do just direct wood to wood bearing connections, sometimes with a few screws here and there just to get some nominal positive connections between things. These tend to be really clean looking. Again, because we can fab things to pretty tight tolerances, like getting everything to fit up can be quite, relatively reasonable to do. And again, this just goes together in the field really quite quickly. Even doing things like, here you see an example, the photo in the middle, where we've routed in a recess for some intumescent fire tape. So again, a lot of fire considerations at a joint, making sure that where things come together, that you don't have opportunity for hot gases to pass through the connection. A lot of times now we're dealing with that with this sort of intumescent tape type detail. So even recessing that in so that everything can kind of fit together nicely. These types of connections are really pretty elegant and cool. So I think now we're going to switch again. So Michelle can talk about 475.
Yeah, so 475 West 18th Street was a project that some people may have heard of before. It unfortunately was never built, but this kind of represents some of the early wave of these mass timber projects in the US. So this was a project by Shop Architects. It was intended to be a 10-story high-end residential building near the High Line. You can see some of that view here. Really beautiful concept, really beautiful renderings that you can see here. And this was actually part of a the U.S. Tallwood Building Prize that happened back in 2015. So at the time, there was a competition put out by the Binational Softwood Lumber Council, the USDA, and the Softwood Lumber Board to provide some grant money to allow for additional design work and research and testing for taller mass timber buildings. And there were two winners. The West Coast was the Framework Project, and on the East Coast was 475 West 18th Street, and the client group was 130, 134 Holdings. And this, neither project, unfortunately, ended up being built, but they actually both kind of really spurred a lot of the interest and research and the momentum that we're seeing now in mass timber. So and Carol mentioned that there will be some programming related to these early projects as part of the exhibition, and these projects are included in the exhibition at the Skyscraper Museum now. So looking at this project, it was at the time pretty revolutionary in that it was trying to go 120 feet and 11 stories. Looking back at what Tanya presented, about codes. So at the time, the codes only allowed up to 85 feet and 6 stories. Now this actually could fall under a Type 4B construction type with some tweaks. And but that idea the concept didn't even exist. Even the thought of that didn't exist back then. And we were actually trying to permit it under a Type 1B construction. The project had, high ambitions of being as very mass timber focused. So CLT shear walls, glulam beams and columns, CLT floor plates, and all of that was sitting on a concrete substructure, which again is pretty normal. With, just looking at what that floor plan looked like at the time, again, it was residential, so we were able to have some fairly shorter spans, and some of the expectation of having an exposed glulam column in the space was even was kind of encouraged because it was providing that beauty that you saw in some of those earlier renderings. And there was a lot learned on this project, but one thing that I wanted to share today was really thinking about the sustainability story, the embodied carbon story of this project at the time, which was part of the selling point. And most of these high-end residential buildings condo buildings that you see going up all over the place in New York, the standard way to build them is concrete flat slab. So we did an alternative design for that building. We had a full design in mass timber, and then we did an alternative design in concrete, and it was redesigned to be efficient for concrete. We were trying to make it really a like for like comparison in terms of what you might actually build in that space. And you can plug all this stuff into your embodied carbon calculators, and you get something that looks like this. So the dashed line above is the concrete option. The solid line below is the timber option, and you're seeing, that there's much more embodied carbon when you use the concrete, or with the concrete option. But one thing to keep in mind with a lot of these tools is that there are a lot of assumptions that are made in any life cycle analysis, and that's something we're also learning in this process. So if you go back and plug kind of rethink some of your assumptions in your materials, you can actually end up with a situation where your timber option could somehow end up looking worse than concrete. And that really is in several, there's a few steps here. So, your wood needs to be most importantly sourced from replenished harvest areas. And if you're not sustainably sourcing your timber, then, this sustainability story isn't great. But, for the mass timber for the way that the market currently is and how the big mass timber suppliers are right now. We have fairly strong forestry practices and sustainable forestry practices happening, but it's something to keep an eye on as the industry grows and, where those shifts could be happening. There's also a lot of energy that can be used or lost in transportation. Concrete is usually pretty local, so we do have to be cognizant of where some of our timber is coming from. On the East Coast, some of the options might be coming up from the Pacific Northwest or from Europe. So just something to keep in mind. And then also looking at, your building end of life. Again, even if you have your sequestered carbon, if you're really looking at this towards the end of life of building, you might end up in a situation where you're releasing much of it back to the environment if you're not careful with the, how you're disposing of a building. So, this project, which will, can go into much more detail in follow-up programming, was, one of the leaders along with the framework and really kicking off this interest and digging into some of the sustainability aspects and comparisons at the time. And then, that led to some of the projects that we're seeing now. Oh, and actually, sorry, just some lessons learned there, but some of the projects that we're seeing now, and one good example of that is Ascent, which came several years later and had a different outcome, and that it was built. So I'll let Tanya take it from here.
Okay, so we'll wrap up. I'll talk a little bit about the Ascent project. So this is a multifamily residential building in Milwaukee, Wisconsin. It was completed about a year and a half ago. So we were the mass timber supply partner on this project. It is 25 stories. It's a 19-story timber structure over 6 stories of concrete parking. It is currently the tallest timber building in North America. This one, I'll talk a little bit about code in a second, but sort of on the sort of in contrast to, Michelle mentioned that for 475, they were planning to go as a type 1 B building with a material variance. This was the opposite. We worked with the city of Milwaukee and decided that it would actually be a type 4 building with a height variance. Because again, this is way beyond what is permitted by the code. Even in the new, the new 2021 IBC, this wouldn't be permitted. So it's just a reminder that there is always, of course, the alternate path of working with the jurisdiction to get something approved. So it is, the lateral system is, excuse me, concrete shear walls, but then the gravity system is CLT, glulam post and beam with CLT floors. About 50% of the timber is exposed to view. And there was some interesting things about the fire testing that I'll get into in a second, but just talking a little bit through some of the early design assist process of really trying to refine the design. And I think this is important on a mass timber building, of really getting your trade partner involved early to give feedback on sort of what is going to be efficient and how do you make the building more efficient. So one example of that was kind of reorienting, the CLT spans and the beam spans so that we could reduce the CLT spans. So the initial design had CLT spans in the 20 to 25 foot range. And in order to get that to work with a 5-ply CLT panel, the original plan was to make the CLT composite with the concrete topping. Hit the wrong button. By reorienting the beam so that we could get those CLT spans down, that eliminated the need for the concrete composite. And that really, that helps save a lot of money because you pay a lot of money for those screws to get the composite action between the CLT and the concrete topping. Also just being thoughtful about, as I mentioned, for 2 and 3 hour fire ratings, you're getting a pretty significant char layer. So really thinking about where the timber wanted to be exposed and then paying for that extra fiber to upsize the member, but where it didn't need to be exposed, back of house areas, kitchens, bathrooms, hallways, you don't necessarily want or need the timber exposed there. Knowing that timber is going to be behind finishes, then not sizing those members to char really also helped reduce the amount of wood fiber in the project. And that's really one of the primary drivers of cost, is going to be how much wood fiber you have. So we're always really trying to get that fiber quantity down. And then again, back to the idea of connections, of just really simplifying the connections, figuring out ways to eliminate extra CNCing, eliminating things that require you to flip CLT panels upside down to CNC them on both sides. The simpler you can make those connections, that also tends to have a big impact on the cost of the final design. In terms of code approvals and fire, again, as I mentioned, this was way beyond what was permitted. Milwaukee was not on, obviously, the 2021. It was only completed in 2022. So this is all pre-COVID. There's no taller height limits in the code at this point. And there's no right or wrong answer to this. This is really just about having a conversation with your jurisdiction, with your DOB and the fire department. And the strategy here was to permit the building as it's a type 4 building with a height and area variance. And in order to get there, there's pretty significant testing that was done. So that included 2-hour tests for the CLT panels because the floors needed a 2-hour rating and the columns needed a 3-hour rating, which was really a first of its kind test that was done in North America because that char method that I alluded to, that's in the code that tells you, okay, for each hour of char, you subtract so much material from your section, and then you check the remaining section. Well, that method in the code is only valid up to 2 hours. So if you need a 3-hour rated anything, you can't just use the char method. You have to do something above and beyond. So here, we actually tested, we did 3 tests with different, because at the time we weren't sure what species we were going to be using. So 3-hour tests on columns of a European spruce, a North American spruce, and a North American Doug fir. Fortunately, the tests all sort of bore out and matched pretty closely to what was already in the code, but it just sort of gave that extra level of security. Since your columns are holding up the whole building, they're a pretty critical component, and just making sure we could rely on that 3-hour rating. And then finally, just kind of unique in terms of the supply and procurement. In the end, we did decide to procure from Europe. So, there are pros and cons to every decision. On the downside, you do, of course, have things like exchange rate risk, right? You're buying things in euros, not US dollars. You have to work again with the jurisdiction if it's a manufacturer that does not have North American approval, which is pretty common for some of the Europeans do now have approval according to the North American standards for their glulam and or CLT. But in this case, that wasn't true for the glulam. So working through that with the city as well. Obviously there's more logistics to think about and transport. You're transporting over the ocean in containers, and how do you account for that to make sure it all goes smoothly? And then that the European spruce, the fiber itself is somewhat not quite as strong as, say, an equivalent, say, Douglas fir that you might get from the Pacific Northwest. So the members will be a little bit larger. But really the decision was based on cost. It was much more cost efficient to supply from Europe. And I think, again, because the Europeans have been doing this for quite a bit longer, they do tend to be like a little bit more efficient. And so that was what drove the decisions. But again, it was there were certainly a lot of finding the right logistics partner is a really big deal. I never thought I would know so much about shipping containers and trucking and all the kinds of things that I never used to think about. This all happened, of course, during COVID as well. So shipping routes, the way we thought we were shipping it was not the way we shipped it in the end. So, but we made a success of it in the end. But there was definitely a lot more legwork on the planning part than we thought. So I think that's we're right at about 10 to the hour. So that gives us a little time for questions.
Thank you so much, Tanya and Michelle. Really, such a rich experience that you've had, and the organization of all the material is really mind-boggling. Really, there were a couple of questions, so I'll read them off to you, and I think some of them are a good way for us to understand that while we've had Mass Timber 101 tonight, we might need a little bit more of 100 instead of 101, because one of the very important questions that was asked is, what is the lifespan of mass timber versus concrete or steel? Which is going to give you the opportunity to talk about the end of life, recycling, and the other issues to which you alluded to only in graphs.
Yeah, so there are timber buildings out there that are 1,000 years old, so they can if designed and maintained and properly, they can last, just as long as steel and concrete buildings. I think in our modern way of building, a lot of the design life of buildings comes down less to the actual like materials that you're using and more around whether that building becomes obsolete for program reasons. And there is, I think as an industry, we have to think more about getting more life out of our buildings, extending the life of our buildings. And actually something we didn't talk about at all, but that is a really good application of mass timber is actually in adaptive reuse of buildings. So, a good example is ADM in Washington, D.C., where 3 stories were built on top of an existing concrete building, which also allows you to keep some of your, extend the life of an existing building with a lightweight material, being placed on top. One of the benefits of mass timber is that it's lightweight. So, there's not necessarily a number that can be placed on the lifespan of a timber building, but it certainly can be detailed to last, an equivalent of any of our kind of modern design life of buildings.
Yeah, you
A
really
key point though is to keep it, dry.
keep it dry. I was just gonna say, you can put timber outside. It's not going to last as long as it will. If you keep it dry, it will essentially last forever. Like Michelle said, there's, wooden pagodas in Asia that are 1,000 years old and, still standing. So, and that's pretty much true. I mean, there is really almost no maintenance-free material. Like you're always maintaining a building. So if you detail it right and maintain it right, it will last way longer than you'll tear it down for some other reason other than that it doesn't last. You'll decide that you want something different or,
Yeah.
Well, let me ask a prompt with a few more questions that are super basic, but I know that there are things that I didn't understand as I was approaching the material for the first time. And part of that is just the nature of the role that the computer plays, not just in the design process and the 3-dimensionality of that, but also with the CNC cutting, Tanya, that you referred to. And so I think some people may need to understand that better because it seems to me that the analogy for timber buildings is couture. That it's not really ready to wear. I mean, it's 2x4s and the mass-produced T-shirts would be one thing, but a mass timber building that is designed by an architect, that is engineered as a special project, it becomes a massive 3-dimensional puzzle that needs to be fabricated, and is so specialized and so specific that is a unique product, not a mass product. Am I wrong?
Yeah, no, I mean, I think one thing we didn't get into as much is, one of the big benefits of mass timber is the ability to prefabricate all of these elements and have it come together very quickly on site because you've CNC cut all of your pieces to fit together. You can have things that are kind of going together almost like a piece of furniture, but in order to leverage the ability to CNC cut all of, your connections and all of the penetrations for mechanical systems and everything else in a building, you do need to have designed and modeled that in 3D at a high level of detail, and in many cases higher than you maybe would normally. So, but you can, you might need to front load a lot of your design, mechanical, electrical, plumbing, engineering, design coordination, and get that all into a 3D space so that you can actually really take full advantage of the kind of CNC capabilities and get everything fabricated.
Yeah, I think there's in the industry that there's this sort of gap sometimes between, like you were saying, you start out with these, you start out with this sort of mass produced element, a panel or a stick of glulam, if you will, and getting it from so you've got manufacturers that want to just pump out engineered wood product and sell it. But in order to get from there to a building, no matter how much we aspire to make things sort of simple and repeatable, there is an element of bespokeness, like there always will be. Like every building is unique. So bridging the gap from these sort of rough, or not rough, but like the basic engineered product to get to the fully 3D modeled thing so that it can be cut and so that it can go together precisely in the field. Like I think that's sometimes where the pain happens if you don't have the right sort of mindset or the right team or the right, or even the willingness to, I mean, I don't know why this should be true, not just on timber buildings, but like we have the ability now to build it twice, right? We build it in a model and then we build it in real life. And so it's always been a mystery to me why in most buildings we don't coordinate the MEP until we're in construction. Like that's bananas, totally bananas. And not just in a timber building, in any building, it's bananas, right? But that's what we do. I don't know why. It just seems like there's a culture of like, well, that's the way we've always done it. So anyway, I'm kind of rambling off on a tangent now, but yeah, I agree. I'm trying to say, yes, I agree. There's like very important things that happen in that space to get you from the t-shirt to the,
Well,
to the couture.
since we're nearing the end of the time, maybe you could both talk a little bit about what you think the immediate future and the longer term future of the embrace of mass timber at larger scale construction. How it has been a slow start really for 10 years. If you compare the trajectory of steel construction or early concrete patents in the 1890s, steel takes off. Steel wins the day for the 20th century. Does mass timber have the potential to take us into the middle of the 21st century, the later 21st century as a dominant material, the way concrete took over from steel, and maybe mass timber would take over from concrete?
I think my view is, that we're in the kind of business as usual right now, as most projects of scale are either considering steel or concrete, and usually we'll at the beginning think about both and choose one to move forward with. I think we are going to get to a place where timber is one of the three materials that you look at and make a decision on your project, and really that's as we get larger, it's really in a hybrid setting, right? Is that a concrete core? Is that a steel frame with mass timber floors? Like I think it just becomes a much more common part of our palette of materials that we have available to us. I think the immediate term future, though, I believe we'll be seeing a lot more buildings that fall into those three new building categories that Tanya brought up in the code, and that really brings a path forward for people to build as of right in their jurisdictions these kind of mid-sized projects that I think will just give a lot more familiarity, comfort level in the industry to the point where we can then maybe start making bigger step changes. But I don't necessarily, I mean, this is my personal view. I don't necessarily see a world where timber is the dominant material, but I think it becomes a very key player in our kind of standard suite of materials.
Yeah, I think there's still going to be, different materials are going to still have their place. Like, I don't think it's going to completely replace concrete or steel. I don't think that's feasible, but I think, and I think part of the reason it's been a little slower, like if you look back, the analogy you talked about, when steel sort of took over, when early days of concrete, I think one of the challenges that we have today, it's not necessarily a bad thing, but think of like the codes and the regulations that were in place 100 years ago. The code was like this, there was a book that was like this thick, and so there just was a lot less regulation. I'm not saying it's bad that we have those regulations now. It's just we're in a different time. And so innovating, I think now is a little bit harder because you can't just kind of cowboy your way and do whatever you want now. So I think that's why it's been a little bit slower. But I do think, that there's a really big chunk of market share, if you will. I think there's a lot of things that could be built out of timber that aren't, just because it's new and unfamiliar to people. So I do I do think that it's going to continue to grow. I think the supply chain is going to continue to grow, which is needed if it's going to keep up with demand. So that's kind of where I see it going.
Well, since you mentioned cowboys, Tanya, I do want to call attention to this is Women's History Month, and I felt a little self-conscious that we weren't doing an event for specifically for Women's History Month. But in fact, all of the people who have spoken in the month of March so far have been women, and in this field of mass timber, which is rather unusual. And so I wonder if you might want to reflect on that. Michelle is teaching a class in mass timber now at Cooper, and I'm curious about the proportion of men and women in that class. When one watches most of the conferences, the mass timber conference that has been kind of institutionalized in the Pacific Northwest, and from the video that's at the back of the room, you see nothing but men's heads. So could you talk a little bit about the industry and how you fit into it, and whether it embraces, all people equally, or whether you are fairly unique, and why you got into it in the first place, if that's the case, if you are unusual examples?
Wow. Yeah. So it's, I think, yeah, Tanya and I actually, I didn't mention this, but Tanya was the peer reviewer on the 475 West 18th Street project. So we met, a decade ago on what was my first mass timber project at the time. And, there are examples of a lot of leaders in the mass timber space that are women, but as you noted, I mean, just more broadly into the industry, and particular also in like a lot of the suppliers, it's definitely a male dominated field. But I've certainly felt kind of open arms to everyone. Anyone who's like enthusiastic about mass timber is definitely welcome in the tent, is the impression that I get. It's a kind of a small world that's very quickly growing. And in terms of like the more broad industry, I've definitely seen a shift. Like my students at Cooper, which is an engineering class, is about 50-50, which is a big change from when I was in school. And I think there's a general kind of shift in the industry of more gender equity and different voices. And I guess I will say though, personally, I did have an example in that my mother's an engineer, so I I had a strong female, I guess, role model from an early age that made it not seem too intimidating to kind of get into the industry.
Yeah, I also I mean, to me it never can change fast enough, because I think it's such a great career, and I do hope to see it improve in terms of gender balance over time. I mean, also at my alma mater, I got my engineering degree at UT Austin, and they are now, their undergrad classes are roughly 50-50. So I think that's a big win. I think retaining women as we go through the profession is important. I think that's, it's not just about the pipeline, but it's about how do we create an environment where women can thrive and want to stay rather than leave the profession or what have you. I will say, one of the things I've noticed, we always, in the mass timber world, I think sometimes we feel like a little bit inferior to Europe, because it's like, oh, they've been doing it so much longer. But I will say, I have definitely noticed there's just way better gender balance in the North American wood world than in the European wood world. Like, you go to the European wood conferences, and that is really like all dudes. Like, so I do feel like we are doing that better than the Europeans, which makes me kind of happy. So yeah, hopefully we'll continue to improve. And it's great to have, like Michelle said, like I've known Michelle a really long time, and it's always been really great to have, just see other really smart, capable women just doing what we do. So yeah, makes me proud.
Well, one thing I've noticed about the mass timber communities, it's incredibly sharing and welcoming. And maybe that's a characteristic of women. I'm not sure, but you guys, if I use that phrase, have been really, so wonderfully generous and instructive and intelligent tonight in the conversation, bringing such beautiful organization, but also personal experience to this. I'm sure everybody values it as much as I did. So thank you everybody for joining us tonight, and thank you so much, Tanya and Michelle, for starting us off on a semester which is still evolving, but we will certainly be talking more about the two projects that you mentioned. The project's West 18th Street, and also Ascent, and a lot of the architecture in between that has been explorations in some of the most important and innovative examples of mass timber here in North America. So thank you so much for starting us off tonight, and I hope I'll see everybody else next time. Stay tuned on our website in order to hear what's next up, and enroll in our eBlast newsletter if you want to stay informed. So once again, thank you everybody for a great evening and a great
Thanks,
course.
Carol.
Thank you for having us.
Bye everybody. See you next time.
Bye.
Bye.